Takes it. Yeah. Hello, everyone. Welcome to our mechanics seminar, the second talk of this term. It is a pleasure to have today our speaker coming from the University of Connecticut in the United States, George Matheou. George is a graduate from Caltech in the US, where he got his PhD. And before that, he did his undergraduate at the University of Athens in mechanical engineering. And today he's going to talk to us about modeling, modeling atmospheric turbulence, large eddy simulation of the atmospheric boundary layer. George, it is a great pleasure to have you with us today. Please go ahead. You can share your screen and start your talk. Thank you.
Thank you, Yuri. It's very nice to be here, virtually, at least. And I'm hoping that we'll get the chance to meet everybody and interact in person as soon as possible. So you guys can see my screen, I am assuming. Yes?
Yes, it's fine. Yes.
Okay. So if you lose me or anything, please let me know, because it did happen to me once last year when I was teaching my class virtually, that I was talking for 10 minutes and I was on mute. And after 10 minutes, somebody said, "Hey, professor, are you talking to us?" And I'm like, "Yeah, sure. Who am I here to talk to?" So just feel free to interrupt me for anything. I cannot see the chat, so just speak up. Or you need to alert me about this.
Yeah, I will. If someone raises the hand, I'll let you know.
Okay. So I am George. I'm in mechanical engineering at the University of Connecticut. Right now, I am I'm like many of you, I am at home. So there's maybe going to be like some interruptions during this whole thing. I'm sorry in advance for this stuff, but this is kind of like how we live these days. I'm going to talk about some of our kind of like work we're doing on modeling atmospheric flows. This is going to be a little bit of like an overview. I'm not going to go into like many details. You can go on our website to find some of the papers and get more details. You can go actually on we have like this little bit of like this social media Twitter account that we use sometimes to tweet like some of the images or videos we produce. So if you want to grab any of the material or our images or videos, these are free to everybody on our website, on our Twitter. Just go ahead and do it. No problem at all. Even the computer code is available on our website. This is work I did with other people, and our work that I'm going to present over some time now. So there's a lot of people who and colleagues and friends that they kind of like put their input here. When I was at JPL before, and now right now at the University of Connecticut, my students and postdocs that we work together. And I would just mention maybe one name, Daniel Chang, who was with me at JPL before at Caltech, that we did some of this work together when we were both at JPL. So Daniel is one of like the person who I'm kind of like going to kind of present a lot of his work today, some of the stuff we did together. We're very thankful for everybody who funded us over this time and gave us a lot of computing support. So I'm going to talk about the atmosphere and a little bit of climate and weather. So usually these talks, when we start talking about climate, they start kind of like in a bit of like a pessimistic way. So I want to avoid this. So instead of kind of like giving the usual introduction to this problem, I'm going to try to, together, if you guys can help me, kind of solve a little bit of like a problem. So there is all this talk about climate and the temperature of the planet rising. So what we're going to do together, hopefully, is to do a very, very simple calculation. So the calculation is going to be like this. So we're going to compute what is the temperature of our planet. So we're going to compute the temperature of the Earth. And this is called it's going to be like a mean temperature of the surface. And when I say mean, I mean day, night, all seasons, kind of like take the average over area and time. And the calculation is, if you want to find temperature, the calculation is pretty simple. We're going to do this energy balance, energy input equals energy output. So all of our energy that we receive here on Earth, almost all essentially, comes from the sun. So the sun radiates about 1400 watts per square meter. This is something that you can kind of like go measure in space. This pi r square is the cross section of the planet. Like this is what we receive, like on if you're looking at our planet from one side. And then this guy here, this 1 minus alpha, this is something that's very, very important in this talk, and we're going to come back to this guy over and over today. So this alpha parameter is called the Earth's albedo. And what this means is that when the sun sends energy to Earth, about 31% of the energy gets reflected back to the space, and it doesn't interact with our planet at all. Okay, so albedo is a Latin word, and it means whiteness. So the whiter the planet, or more scientifically, the more reflective the planet is, the more energy is reflected out to space, and the more energy ends up getting absorbed by our planet. Okay, so if the way this works is that if we paint all of our roofs white, we increase Earth's albedo, okay, and we receive less energy from the sun in the end. Okay, so this is energy in on the left side, and on the right side is energy out. And we're going to assume that we radiate as a black body. The planet radiates as a black body. So this is a surface area, Stefan Boltzmann constant, and then temperature to the fourth. So we're after this temperature, essentially, the temperature that we are to radiate so that we're kind of in equilibrium. So this is called the mean surface temperature. And if you do the calculation, you are getting about minus 18 degrees Celsius. So this is a bit on the low side. And this is, again, it's like the mean day, night, all seasons, all of the planets. So the real number, it's about 20 Celsius. So we're a bit off. So this is too cold. So I don't know if any of you guys have any ideas why our calculation is a bit off. So now you can jump in and tell me what you guys think.
There is no atmosphere on this calculation.
Yes, Yuri is right. So there is no atmosphere. So this works only for basically a rock that is kind of like flying into space, more or less. So we have neglected in this calculation the atmosphere. So the atmosphere is a very complicated thing. And in reality, the atmosphere is really like a processor of energy. And what you see here, these numbers and the colors of these arrows is the types of energy flows that are happening in the atmosphere. Again, this is mean day, night, all seasons. Okay, so this 341 is the incoming solar radiation. So this kind of like orangey color here, this is mostly solar radiation. So this is the visible wavelengths mostly. So this is the short wave radiation. So this 341 comes in, it gets absorbed by the atmosphere and the surface, and then you see about 102 watts per square meter is getting reflected out from the system. This is about 31% is the effect of this albedo effect, right? So this stuff, they just hit the clouds mostly and the surface, they get reflected out of the planet, they play no role. The rest is absorbed, and then it's kind of like getting moved around inside the atmosphere. It's radiated outside this reddish color here. This is essentially infrared radiation. It hits the clouds. Some clouds send it back to the surface. Some wavelengths, they go through the clouds. There is latent heat. There's also a sensible heat that is going on. So these numbers are kind of like rough numbers. They're not, it's very difficult to make these measurements for many, many reasons. But you can go in space, and then you can kind of try to measure what is going in and out. And these measurements these days suggest that there is currently an imbalance of about half a watt per square meter of more stuff coming in than stuff energy going out. Okay, this is a rough number. It has a kind of like an error bar. And it's not a big number, because if you're around in Brasilia around noon, you go out, you're getting hit by 1,000 of these units. So the balance is not very big, but it's going on for such a long time that it's starting to kind of like change whatever is happening here in the atmosphere. So because of this imbalance, everything inside the atmosphere and our planet in the full climate system is now in the process of readjusting. Okay, if you guys have any questions, just let me know. Jump in. It's okay. We can spend as much time as you want on questions, and no worries.
George, I have a quick question on this on the previous slide.
Yes.
So you're making the balance from the atmosphere point of view. I can see radiation, well, energy coming in, energy coming out, and I see surface radiation, all interaction between the atmosphere and the surface. How about the ocean?
So the ocean, when this arrows stop on the surface, then there is and these guys that they seem to be coming out of nowhere, this evapotranspiration or the thermals. There's also like the ocean that is kind of like below the surface, and it's modulating this stuff here.
So it's not a major number. So it is this 80 plus 17 and not a number like 390 that I see on surface radiation. It is a small contribution.
So it's so when this says surface, it actually means the ocean as well, not just the land here.
Oh, I see.
So these are average numbers, day, night, all seasons, everywhere.
Okay,
so
all right.
When we say surface, here we mean ocean, we mean snowpack, like the Arctic and all of this stuff. Like everything is getting kind of like lumped in together here.
Okay, gotcha.
And so remember, so this is a good question, Yuli. So we started with this. So we started with something that is a radiation problem, and I'm not a radiation expert. I'm more like a fluid mechanician kind of person. And then we agreed that it's more like a fluid mechanics problem, because radiation, yes, goes in and out, but the atmosphere is kind of like a big processor. So all of this stuff, the atmosphere is made of mostly it's a gas, and the ocean, like Yuli says, is made of liquid. So this now becomes not so much a radiation problem, but it becomes more of like a fluid mechanics problem in this case. And radiation and fluids, as we're going to discuss later, they're a little bit linked, so it's not completely independent. So now we're going to go in a step deeper, and we're trying to understand what is happening in this big processor of energy, our atmosphere. So when we talk about the atmosphere and climate, there is two important concepts. So the first concept is the forcing, and the forcing comes from greenhouse gases that they are injected into the atmosphere, and they are well known that they absorb radiation and they raise the temperature around them. So carbon dioxide is about 48% now more than pre-industrial levels. Methane is a bit more intense. It's about 148% more in our atmosphere now since about almost 300 years ago. Okay, so this is the forcing. And the forcing is the story with the forcing is pretty straightforward. You can measure how much warming you get by having carbon dioxide in your diluted gas and things like that. But the problem is not the forcing. The problem here is the feedback, because water vapor, and water is very, very abundant on Earth, is also a greenhouse gas, but we have no control over the amount of water in the atmosphere because of thermodynamics, because of transport, because there's so much ocean. So this now comes into the issue of feedback. So we put greenhouse gases in the atmosphere, but also water vapor is a greenhouse gas, and this creates funny feedbacks in the system. And to make things more complicated, clouds, as you can see from, if you look outside, clouds can be like very bright, so they interact a lot with the radiation. And clouds is basically water vapor that got condensed into ice or water, liquid water. Okay, so how are scientists trying to kind of like figure out what is happening? One of the things that they try to do is they try to kind of like figure out what is the sensitivity of the system. And to figure out the sensitivity of the system, in this case climate, you do two runs with your climate model. You do one run at sort of like nominal conditions with present day carbon dioxide levels, and then you double the carbon dioxide in the atmosphere, and you run again your climate model, and then you figure out how much is the temperature change in the atmosphere, actually on the surface. And this number, this difference in the temperature between these two runs, nominal and double carbon dioxide, is called climate sensitivity. And I have this plot here. It's kind of like old, but it's very, very, it's very useful. So I'll keep using it, even though some of these numbers now are a bit outdated, but they haven't changed a lot. So the issue is still there. So here, with every one of these bars is the climate sensitivity as predicted by a different climate model. So each bar is a climate model, and you can get kind of like numbers that are around 2 Kelvin, which is it's kind of like mostly okay. But if you are getting into like the range of like 5, 6, maybe 8 sometimes, I mean, this is like really bad news. So if climate sensitivity is like 8 Kelvin, it's like not good news for anybody. Okay, so here you see the models having a bit of a range, and then you ask the next question. It's like, why are you getting this big range? Well, what is changing between this model, like the red one that has low climate sensitivity, and this blue one? And when you go look at this change in the model, you see that there is this pulse here of the globe. Hopefully you can see where I'm pointing, that if you have high climate sensitivity, then the model here in these blue regions is evaporating cloud. But here, if you have low climate sensitivity, the model in these areas here, it's actually producing more cloud. And these are clouds that they form at the western boundaries of the continents. And these are low clouds. The clouds look like this. So this is like an actual satellite picture of, this is the west coast of California. This is Mexico. This is Baja. And there's like this cloud deck that sits very, very low to the surface. It covers the surface, and the ocean, the natural color of the ocean is very dark. So its albedo is basically 0. But when it's covered with the cloud, the ocean becomes, the surface becomes very reflective. The albedo is almost 1. So this, producing this cloud or reducing it, makes a big impact on the reflectivity of the planet, and this leads to feedback. And the bad news here is that if you look at this color bar here, this change between the two kind of like extremes here in climate sensitivity, this is like percent cloud cover per Kelvin, and these numbers are like really low. This is like this, we're talking about changes in percent of like 2%, 3% in area coverage of the cloud. So if you're an engineer or a fluid mechanician and you run your model and you find the answer within, like 2%, 3%, and you work in the car industry or even like the aerospace industry, and you get 2% accuracy, it's like, I don't know, maybe you get a promotion. But in this case, we have a very complicated problem that it's difficult to model, and also we need to have like very, very high accuracy. So this is a big problem that has been going on essentially since the beginning of climate modeling about 30, 40 years ago. And there's also always these statements in this in the IPCC, this panel of the United Nations that reviews the literature on the subject, that says cloud feedbacks, particularly from low clouds like Stratocumulus that I just showed you, this is the largest source of uncertainty in climate models. So this is the biggest problem that climate models have in making their forecasts, their predictions more accurate. So what the problem is, how to kind of like figure out how much of this cloud is changing, this stratocumulus cloud is changing as the climate is warming or cooling in general, or in our case, just warming. And this is an issue that many times you can find it into the mainstream press. I have some This is the front page of the New York Times. Here it's calling about the clouds effect on climate change. The Economist has many times like talked about this issue. I mean, this is one of the nice sentences that they had. It says, the greatest mystery is the effect of human activity on clouds. Okay, so this is like the real problem in climate science. And okay, so now we are going to see how, as scientists or engineers or mathematicians, we can contribute to this problem, right? So we're asked to simulate this system, and in this presentation, we're just going to talk about the atmosphere. The ocean is also very important, but we're kind of like going to neglect it for now to make things a little bit simpler. So let's say you want to simulate the atmosphere. So if you're a climate model, or what we're calling global circulation model, or GCM, what you have to do is you have to simulate the entire planet, okay? But because the resolution or the computing power is you cannot have infinite computer power, you can start from like the entire globe and go down to resolution of a few, in these days, like the maximum resolution is like maybe like a few kilometers. In a little bit like the older days, climate models had a resolution of about 100 kilometers. But there is like all this range of stuff that are happening that actually include all the clouds that they have to be parameterized, they have to be modeled. And if you are into fluid mechanics modeling, this kind of modeling here for the atmosphere is what we call RANS, or Reynolds Average Navier-Stokes model. So there is this big gap here of stuff that are going on that the climate model has to sort of like represent without explicitly simulating. Okay, so we need to fill this knowledge here, this gap, and there's also observations, but there's also other models that they can fill this gap. So you can do LES, or large-eddy simulation. You can have domains that they don't cover the entire planet, they cover a small section of the atmosphere, but even with LES, you cannot go down to maybe 1 millimeter. That is like the smallest flow scale in the atmosphere. You still have something that needs to be sort of like modeled. This thing that has to be modeled, you'll see it's more easy to do it because it doesn't include like the entire cloud anymore. So LES, I'm going to show many examples, actually resolves clouds. You can have clouds in your simulation, but there is still a bit of a kind of like a range here that you have to model. So in this case, these models are called subgrid-scale models, or SGS models. And to do this, a lot of the times we would just do like a direct numerical simulation and find out, sort of do like a simulation that resolves all the way down to like the smallest scale in the flow and kind of like gives you some information of what is happening at the small scales. So what I do DNS and LES mostly in my work, and I interact with lots of people that they do actually GCMs. So what we do is we run the LES and then we give them back the results, and they sort of build these RANS models for climate modeling. So this is a bit of like a Russian doll approach situation, where you have one model that is getting informed by the smaller one, and the smaller one is getting informed by another one in scales. Okay, so this is when I was a grad student, my work was not in atmosphere or climate or things like that. I was just doing simulations of fluid flows. I was interested in other things. So then I said, okay, this is very interesting. I can maybe I can contribute into like this knowledge of like LES for these flows, since I knew a little bit of, I was starting to get a little bit of like knowledge into the LES. So this is how we myself got into this this area. So we started kind of like asking these questions of, how the LES is performing for these atmospheric environmental flows, and what can we do to make the performance a little bit better. And unfortunately, the performance for these systems, for the atmosphere, for example, for all the LES some time ago was not quite at high fidelity. And these are a couple of examples here. So this is a simulation of these Stratocumulus clouds. And this is, you start a simulation from like initialize to 0, and then you run it for 4 hours. And then this is like the model spread here, this gray width. And you can see some, even though the expected answer here is cloud fraction of like 1, everything covered with cloud, there are some LES models, particularly way back, that they would take this cloud and essentially evaporate it just by doing nothing. So this was not very satisfactory. And also in other cases where you have clouds that they rain, they precipitate, if you look at the precipitation rates like this one, so each line is a different model, you can run the same case, different models, different LES models, and you would get very, very widely varying results, okay? So this was something that it's very unsatisfactory, and we believe that it has to be, it can be, as you maybe you'll see a little bit later, and hopefully I'll convince you about this. This is something that it can be improved these days. So now let me go back here. So what I'm going to show you now, I'm going to show you kind of like how this process of this Russian doll approach works for these systems. I'm going to show you some direct numerical simulations first, and we're going to extract some knowledge from our DNS, and then we take this knowledge and use it in our LES to build one of these subgrid-scale models. And again, I'm going to skip a lot of the details here. If you want to find the details, you can go and let us know. I mean, we can send you some of the publications, or you can go get some of the publications from our website. So if you do DNS, everything has to be sort of like in the kind of like the fundamental aspect of things. So this is one of these fundamental flows. This is homogeneous stratified shear turbulence. So this is a 3D box. And what you see here is basically one vertical slide of this box. And we have turbulent flow that is driven by shear. In this case, there is very little density stratification. And these cases are statistically stationary. So in these cases, basically shear balances dissipation. So the shear is, in these cases, is throttled. So at all times, it kind of like balances dissipation. So you can have a stationary simulation. The colors you see is essentially buoyancy or density. This is a Boussinesq fluid, so I can say buoyancy, density, or temperature, and all of these three things essentially mean the same thing. We are classifying the strength of the stratification by using the buoyancy Reynolds number, this parameter here. Epsilon is the dissipation, nu is the kinematic viscosity of the fluid, and this n is the buoyancy frequency of the fluid. This is Taylor Reynolds number of like 350. So turbulence is pretty okay. Like it's not fully turbulent, but it's pretty, the Taylor Reynolds number is pretty okay. So this is a case that is closer to being neutrally stratified. But what I can do is I can increase the stratification a little bit. So this is stable density stratification. And what you see here from before, you see that this vertical scale is a little bit reduced now. So all this, before I had these big eddies that they were covering the entire domain, and the domain here is periodic. Now these big eddies, they don't cover the entire height of the domain. They just, they're confined into their own length scale. And I can keep this process going. I can increase the stratification a little bit more. So what you see here is that the vertical scale of the eddies gets more reduced, and you're getting into situations where things are not really kind of like overturning and being turbulent. In these cases of high stratification, you see like all the stuff are most like sliding on top of each other than being very, very turbulent. So there's two things that are happening here. The vertical length scale is getting squished, is getting reduced, and also the turbulent kinetic energy of the flow is also reduced. And if I keep increasing the stratification, then I will get into this state of the flow being partially laminarized, where I get these patches of turbulent flow, but then I get actually a lot of like big regions where the flow is smooth and laminar. And these patches, when you look at the simulation, they are sometimes here, they're very unsteady. They are born and they disappear just randomly everywhere in the simulation. They don't just sit up here, they are kind of like everywhere. So this is actually like the state of the bulk of the atmosphere and the ocean. And where, you know, if you have experience from like flying, most of the atmosphere is it's smooth. Sometimes your flight might get a bit bumpy. So a lot of the times, like you'll hit one of these turbulent patches, or you might hit most likely gravity waves. But this is sort of like the state of the atmosphere away from the ground. And this is again a summary of this sequence of DNS runs. And you can pick your favorite parameter here to describe these simulations. So now I'm showing like both planes. This is X and Z that I was showing before in the movies, and now I have like the other plane, the YZ plane, and you can see how things are kind of like changing as stratification increases. Okay, so first things first, we have to make sure that the simulation is running okay, so everything is accurate. So we are comparing here with some experimental data. This is from an active grid turbulence, and red is experiment, black is our simulation. So the wind tunnel is much longer than our simulation domain, so you can get like lower wave numbers, but the measurement has a bit of like noise floor around here, but in the simulation you can actually go down in energy. So this is like the classical Kolmogorov scaling that you can read in your textbook. The only thing I want to mention here, if you guys are doing simulations and you are comparing with experiments, because in experiments you cannot measure all three components of the velocity at the same time. You have to ask the experimentalists how they got some of these parameters, like their dissipation. You have to make sure that in the simulation you are computing it exactly the same way as in the experiment. Otherwise, you will not get collapse. So this is a nice thing, and this is what we are looking when we are studying turbulence. We're looking for essentially these relationships where we can have data that, in this case, the red is an experiment, and the black lines is a simulation. But if you scale everything with the right parameters, then the data collapse onto each other. So we're going to take this scaling now to the next level. So we're going to understand how our DNS works instead of in terms of scaling, in terms of TKE and dissipation and the length scales. And there is actually like a theory that has been developed a while ago from Monin and Nabokov, and this theory is usually used when you're close to a surface. But it turns out that we can maybe a little bit adjust this theory to scale our DNS results. So similar to what is happening in the surface layer, we can say that this group here, a length scale, the turbulent shear stress, and the mean gradient of the velocity is a universal constant. And then you can go and define a length scale from this constant by setting this guy to 1. This k here is it's one of the constants that they come out of these calculations. This is like a von Karman constant in our case. It's like a generalized von Karman constant. I don't want to get into like a lot of like the details here, but the goal of the DNS is to kind of like inform kind of like this development, to help us kind of understand how things scale, to find these scaling relationships that, as you will see, they're pretty powerful. And I need to again acknowledge here the all the work that Daniel Chang did of like figuring out all of these things. But if you take this the spectra from the DNS, you scale them using our newly derived scaling, and you get them in this form, this non-dimensional form. This is a plot of our DNS, and each line here is a different DNS of different stratification. So red is the most stratified, and then orange less, and as you go to the black, the least stratified. So this line here, the straight line, is basically like the classical k to the minus 5/3 Kolmogorov scaling. So this is our DNS. These are data from like the actual turbulent atmosphere. And I squished a little bit like the axis here of the measurements to get my aspect ratio the same as my DNS figure. And the nice thing here is you can see that these numbers here is exactly the same stability parameter that we have in the DNS. This is atmospheric surface layer. And then you can see how these curves peel off from the Kolmogorov scaling depending on their stratification strength, okay? So this gives us kind of like the hope that this, what we tried here, this scaling theory for homogeneous stratified turbulence works even when you are not in the atmospheric surface layer, okay? This is a straight line in the atmosphere because the Reynolds number is like very, very high. Obviously in the DNS, we get the dissipation subrange and everything kind of like falls down here. This scaling here, it's an outer variable scaling. It's not like the scaling I showed you before that I scale everything here with the Kolmogorov length. Here I'm scaling the x-axis with this outer scale, this z, which is the large scale of my problem, okay? It's a little bit different. That's why all of the hooks here, they don't kind of like align at the high wave numbers. I can do the same thing with buoyancy. I still get a very good agreement with whatever it says in the surface layer, whatever it was measured in the surface layer. And you can keep going, and then you can try to scale all the energy peaks with these variables. And you can see that these are the numbers that Keimal et al. Found like in the early 70s. And again, we have very good agreement with what was measured in the actual atmosphere and from our DNS, okay? So the whole point of this is that I have now basically this blueprint. This is kind of like my scaling, my understanding of stratified turbulence. So I am going to exploit what I have learned here, and I'm going to build an LES model. So when I come back to my Russian doll approach here, so what I found here from like this, the blue stuff, I don't exactly envision running the DNS here, but from this, I extracted the scaling of my turbulence, and then I'm kind of use it to build a model, build a parameterization for the LES, okay? So this is what I'm going to go, this is what I'm going to do now. I am going to do an LES of essentially, in our case today, atmospheric boundary layers, and I want to build a model for the red stuff here that I'm missing. And just for completeness here, I have the full system of equations that my LES needs to solve. So these are the typical stuff in fluids. I have mass conservation, momentum conservation. My energy equation is this liquid water potential temperature equation. So I have like a little bit like it's a temperature equation in this case. I have conservation of water. And if you have rain and things like that, you need to have like extra equation for your hydrometeors. In this case, we're going to just have rain. So we are tracking the number of the raindrops and the total mass of the liquid precipitation phase. It's unsteady term, advection. Hydrometeors have sedimentation, pressure, buoyancy, forcing, Coriolis. There's like some input from the large scales because the domain is it's small. And what I'm trying to do here is I'm going to try to figure out this red stuff here, the highlighted red terms, which is my turbulence model. So what I need to figure out, I need to figure out this tie ij, which is my turbulence stress tensor, and this turbulent fluxes for the other equations, for the scalar equations. And I'm going to base all of my development on this model that is called the stretched-vortex SGS model. This is a little bit different than all of the other closures that are mostly used in CFD. So this is a structural LES closure. It has very nice anisotropic properties that I'm trying to exploit. So the model was already developed for the neutral case. And what we did, essentially Daniel Chang did, is to figure out a stability correction for stably and unstably stratified turbulence. So our goal is to do two things. We're going to change how TKE works in stratified turbulence and also correct for the anisotropy. And we don't want to be messing up a little bit more like the nice physics character of the closure. So the way
George,
the model works.
Can I interrupt you?
Yes.
So I got my connection is not very good. I lost what you said when you were defining the rain number on slide 21, I think. So what is the rain number?
So this n is the number of rain droplets in my grid cell. So I'm tracking in each grid cell. I am tracking the evolution of the total number of the raindrops, and I'm also tracking the evolution of the total mass.
So why are they not the same thing? So why, when you know the mass of rain, so how much water is raining, do you still have to keep track of the number of drops?
Yeah, that's a very, very good question, because there's a distribution of sizes. They don't all have the same size, so
and they do different stuff.
Yeah, so they have a distribution of sizes, and based on the distribution of sizes, you can have same mass but different numbers.
I see.
Different total numbers.
And then rain, I think, comes from the larger drops, and the smaller drops, they get suspended in the cloud.
Right. So
I see.
The liquid gets split in this case in two parts. There is the liquid that is the smaller droplets that are suspended, and that is part of the water equation. And then we split this part into the hydrometeors that they fall, and then these are kind of like they have these sedimentation terms that they are falling fast out of the grid cells towards the ground.
I see. That's this delta 3J, right?
There are different ways of doing this. This is not a unique way. This is how we do it in our model. There's all sorts of models for this.
Gustavo, I think you want to say something?
Yes, just using I think that's the opportunity to ask how do you model this this water? I mean, do you assume a distribution, a size distribution for these two classes of water in your case, or how do you model that?
Yeah, okay, that's a good question also. So we have this this parameterization for what we call microphysics in this field. So the parameterization comes from Seifert and Beheng, and it assumes that the drops they have like a double gamma distribution. So there's many small and many large kind of thing, and so there's a little bit of in each grid cell it assumes a distribution, and based on this on the moments you can figure out the mass and the number. So if from the mass and the number you can figure out essentially the distribution.
Okay, perfect.
So this is a model, like it's fairly okay, but it's still a model. It's an assumption.
Mm-hmm. Okay.
So the n that you model on this rain number, it is actually a distribution. You model the evolution of this distribution, or do you actually model the number per unit volume of?
Yeah. So we solve for the evolution of the number. We don't resolve the distribution.
You assume. I see.
Yeah, we have to assume a distribution so that we can do some of the other modeling that is required, to get the to get the sedimentation velocities or to get like the there's other stuff going on here. Like there's like interactions between the drops, and there's like thermodynamics. Some of the drops are evaporating and things like that. So there's like models for this as well built in these terms here on the right hand side.
Okay, very good. Thanks, George.
So these models are they're quite complicated, and the physics here are very, very complex. And I'm not doing a good job of kind of like, I'm not talking about this now, but there's like very, very rich physics in this in the evolution of the hydrometeors and all of this stuff. I am kind of like neglecting them here. I'm lumping them into this these two terms that I have on the right hand side, but the problem is fairly complex. That's all good questions. Are you guys okay with this? Should we move on?
Yeah, move on. Yes.
Okay, let's move on. Okay, so we're going back to turbulence now. So the model assumes that in each grid cell, and I have like a little bit of like a cartoon of the grid cell, there's like this vortex here in each grid cell that is kind of like wrapping the fluid around it, and there's like a mean large strain field around the vortex. And this is, if you're inclined in this mathematical developments, there's like this great paper by Landgren from like the early 80s, where if you choose stretched spiral vortex, you can, and this is an exact asymptotic solution of the Navier-Stokes, okay, you can extract the spectrum of the velocity field based on this solution. And the spectrum, it's a k to the minus 5/3 spectrum with a bit of like an inertial dissipation range. So everything comes out like analytically from all of this exposition. So if you have the spectrum, you can get the TKE, and then you can get the stress tensor, this tau ij, and you can also get the subgrid scalar fluxes. And a nice thing about the model here is that the subgrid scalar flux vector is not aligned with the resolved gradient vector, this d theta dx vector, because this guy in the front, in a lot of models, this guy in the front is a scalar. So this vector on the left and the vector on the right, they have the same direction. But here, this guy here, it's a tensor. It's a second order tensor. So the sigma and the d theta dx vector, that is the resolved scale gradient of your scalar in the turbulent field, these guys are not aligned, okay? This is very nice. You can see that the model is, it has this built-in anisotropy into it. And when you go compute these things, all of these terms, everything, you can do it on the grid scale. Everything is local and dynamic. And now there's going to be like a lot of math, and I'm going to go through this very, very fast. So we took this model and we said, okay, now I'm going to form a stability correction. So I'm going to find these factors here that they change the TKE and the length scale that are inside the model. And in LES, we usually assume that there is stationary and homogeneous turbulence in each of our grid cell for the volume of the grid cell and the duration of the time step. And when you start this analysis, you have too many unknowns. And as you go on, you have to grind a little bit and reduce the number of unknowns. We have an assumption here about the scaling of the dissipation that is originally due to Taylor from like a long time ago. It's a scaling of the dissipation as a function of the TKE and the yet unknown length scale of the stratified turbulence. You can go here and you can redefine and kind of like repackage some of the stuff so that they can fit into our theory, into our scaling that we derived before from the DNS. And there is this part where you have to make an assumption, like a biggest assumption in this model is that there is this blend of length scales. The delta here is the neutral stratification length scale, and this L is a little bit like a Nabucco length that goes into the stratified turbulence. And when I say stratified here, I mean both stable and unstable. So there is this blending parameter, this alpha, that we extracted from the DNS. You can show that it's the limit of this quantity here as the Richardson goes to large numbers. So we pulled out this alpha from the DNS, and this basically asymptotes to around 5. So we took 5, we put it in our LES, and it works fine. It's not actually very sensitive, so if you put like 8 or 10, it works pretty much okay. And so this is a parameterization that we used. It's originally from Brost and Wingard from like the late 70s. And this says that if you're in stratified turbulence, it's not like the neutral turbulence that you need a length scale to form a Reynolds number. In this case, it's a 2-parameter process. You need a length scale and an aspect ratio. And this is what this relation says here. And again, this was discussed like in the 70s by Brost and Wingard and others. And it kind of like this stuff, they kind of like tend to get rediscovered if you're just reading like the latest literature, but there's all these papers from like the 70s that they're like actually very nice. So I skipped a lot of steps here, but in the end, you can define a Richardson number for the vortex for the SGS field. And this is nice because the Richardson depends on the vortex orientation. So no matter how the large scale field is, how you're fielding the LES, if the vortex is kind of like tries to spin things in the horizontal and gravity is pointing down, then you get no penalty. These are like pancake eddies. The model works as if there is like no penalty. Basically, the model Richardson number is 0. And the opposite holds when the vortex is trying to overturn stuff in stably stratified turbulence. So the Richardson number in this case it's a maximum, and you're getting like the most penalty for your length scale and the decay. Everything we did is local and still dynamic. There is no adjustable parameters in this. We had this parameter here, this alpha, but we set to 5, and we just set it like that. We never change it. We don't change it depending on what flow we're running. So this is a model that doesn't have any parameters. So we always run it as it is. It either works or not. Same thing. There's nothing to tune here. Okay. We start by running again a fundamental flow, this homogeneous shear stratified turbulence. On the left is DNS, on the right is LES, and you can see that the LES is now it's reacting well to the increase of stratification. Obviously, DNS is 2,000 grid points. The LES is much coarser, but it's very nice because even the LES predicts this collapse of turbulence. And now that I have done this, I'm going to try to simulate something that is a little bit more challenging. I am going to try to simulate LES of atmospheric boundary layers. And usually I'm running a bit over time here, so I think I need about like 7 minutes, if that's okay.
No worries. Just take your time. We can carry on. There's no problem. If you need more time, just carry on. No worries.
Okay. So we're going to do LES of atmospheric boundary layers. Every time we do this, the model setup is identical. There's nothing to tune here, and we're going to compare with theory observation and previous model results. And we're also going to look for grid convergence. So we're basically simulating a piece of the atmosphere. It's about 20 by 20 kilometers in the horizontal and 4 in the vertical. It's a finite difference code. It's a fully conservative, non-dissipative scheme for momentum. Sometimes when you have stuff like rain, we use a monotone scheme to conserve water. In this case, when we have Stratocumulus where we have sharp interfaces, we just do quick for temperature and water advection. And it's an exact Poisson solver, third order RK for time. And let's go and look at some of the flows. So the first flow we're going to simulate, this is an unstably stratified atmosphere. So this is a slice of the atmosphere. The ground is warm, and what you see here is the temperature of the air. And you see this is free convection. So what you get all these thermals because the atmosphere warms at the surface, rises up, and hits the inversion here. And in these plots here, we're going to do two things. We're going to check for grid convergence. We're going to run our LES 10, 20, 40, 80 meters. And we're also going to compare with measurements, these black dots. And everything here is a little bit, it's kind of like scaled so that we get into this, so that we can compare with the measurements. But you can see that the LES, if you change the resolution from 10 to 80 meters, it basically gives you the same results for most of the parameters, for most of the statistics. Even in the case like here of like TKE, that only the two final resolutions are exactly on top of each other, still the spread of the LES is much less than the noise of like the real measurements. And this is a little bit of a problem when you do LES of these flows, because the atmosphere is very variable and its measurements are very difficult. A lot of the times you have an LES that is not fully converged, but is still within like the scatter of the measurement. So measurements are, in these cases, are definitely challenging. So now I'm going to do the opposite case. Now I'm going to have like a cold ground and a warm atmosphere. So this is a stably stratified boundary layer, and I'm going to have a bit of a pressure gradient driving the flow in this case. And I get, so this bottom row here is our LES results. And this is one of the models from this paper that describes the case. And we go from 2 to 4 to 8 meters. And you can see that all of the mean profiles are basically like exactly the same. These stably stratified cases are pretty tough to simulate, because there is the vertical length scale is it's not very big. So it kind of like challenges the model a bit, because it kind of like the vertical length scale is kind of like getting squeezed and approaches the grid spacing. And we go from 2 to 8, and we have good agreement. These are results that are, at least a few years back, they were kind of like typical in the literature. You can go from 1 to 6 meters. And if you look at some of the basic stuff, like the height of the boundary layer, you can see that the height of the boundary layer that you would like to know as a first quantity, it changes a lot by, like 100 meters in this case. And a lot of the times I'm getting asked, how are you able to do like 4 to 8 meters and have like all these profiles being like exactly the same? How does grid convergence work in LES? And the way this works is like this. So this is the exact, if I may go back here. So what I'm plotting here is this guy, the potential temperature. So this is the mean, this is the horizontal mean. So this potential temperature is a function of height, but here I am plotting the full 3D field at 2 grid resolutions, at 8 meters and at 2 meters. So the way grid convergence works is that everything is kind of like at the right place. So the yellow on the top is where the yellow at the bottom is, and all the colors are the same. It's just, if you increase the resolution, nothing changes. You're just getting finer and finer scales in the LES. So it's basically like switching from like a standard definition television to like a high definition version or a 4K. Like the programming stays the same, and you are just able to see more details. Okay, so this is how
does the statistics converge as well, George?
Yeah. So the statistics converge, but of course, this is what we want.
So sorry to interrupt you. Go ahead.
Yeah. So these are the statistics. The statistics converge, but sometimes it looks funny how the statistics can be converged when the field is changing. You can do other things with this.
If I may interrupt.
Go ahead, Gustavo.
Hello, Joey. If I may interrupt you,
Sure.
Also a big problem that we have, for example, in the presence of a cloud is, imagine that you have a stable atmosphere, right, in the presence of an inversion. And
yes.
Then we are talking about, for example, and of course, the top of a Stratocumulus cloud is at the inversion, right? And then we have shear, for example, and this is instabilities at the top of the cloud. So have you studied that
yes.
kind of thing?
Give me 1 minute.
Okay,
We're coming
sorry,
to
sorry.
that.
Okay.
Well, yeah, it's yeah, we will in 1 minute. We're going to talk about Stratocumulus. And I'm sorry again for being a little bit like running over time.
We are asking too many questions. Don't worry, George. It's not your fault. Go ahead. Go ahead.
Okay, you can look into the theory as well. You can scale. You can ask for scaling from like the LES of these stratified boundary layers, and these are different stratification conditions. These symbols. You can see that the LES is doing pretty well. We're not imposing this scaling into the LES at all. In this sense, it's built into the parameterization, but it's not imposed in any way. So this is kind of like the output that is independent from the input. This is Maria Schnider's work. We still need to kind of like publish these results. And now we're going to go into like cloudy cases. And this is when we do LES these are shallow precipitating clouds. This is a picture from the LES. So we gave the LES output to Anthony and Zeng at JPL, and they ran their radiative transfer code on the LES data. And then what they got is this. This is basically like a contour of radiance. What you see here, this is basically what your eyes see. Your eyes are making contours of radiance in the short wave all the time. And this black stuff are the shadows of the clouds on the ocean surface. And you can see, like this, there's a little bit of stratiform at the top and things like that. So this is an example of what you can do today with modeling and CFD. You can get this stuff that they look like very, very close to reality. And this is like looking at the clouds from the top. Everything is dynamic in the LES. Everything is moving. So we have these clouds that are moving. Same case as before. These are clouds that are moving. They produce like stratiform at the top of the boundary layer. And initially when we ran this, we had some issues with rain. And this is when we use one of the standard models in the literature. This is Smagorinsky model. And now this plot is surface precipitation rate. This axis here is time from like 0 to 24 hours. So when we ran this model back in the 10 years ago, and we changed the resolution, we're finding that the surface precipitation rate was changing by a lot. And this, of course, was not satisfactory. The observations are where this black triangle is about like 40 watts per square meter at the surface. So if you look at this, you're thinking, oh, like this model that we were discussing before about the rain and everything is messed up. So it's giving me bad results. But in reality, and this is how we started this conversation, is that turbulence kind of like modulates everything in this system. So sometimes you're getting an error here in the surface precipitation rate because your turbulence modeling is not okay. So you're getting these errors because the system is very nonlinear in other things rather than where you expect them to. So we run the same simulation again. We run our new model. Nothing changed, same rain microphysics, and now everything's fine. So we have to be careful sometimes in these systems because the problem shows up someplace else rather than where it's starting from. And this shows up in the rain field, but it's kind of like driven by the turbulence. And now it's okay. So now we have this. We have the LES, and you can do a lot of things with this. And now we're going to have a little bit of fun with cloud physics. So remember in the beginning I said there's like these Stratocumulus clouds, and they're very important for climate, and we want to understand them a little bit better. And I also said that it's a radiation problem, but turbulence and fluid mechanics kind of like modulate everything so that radiation can work on this stuff. So here we're trying to create like a direct link between turbulence and radiation by looking at these stratocumulus clouds. So I'm going to start here with some of the observations, and these are observations from one of like NASA's instrument on an aircraft. So these are stratocumulus in the Atlantic, and you can these are like really nice data, and you can see the stratocumulus structure, and you can what you see here is that I don't know if you can see this on your screens clearly, but there's like these big lumps of cloud that they look like these big cellular structures, but there's also like these thin regions, these black thin regions that hopefully you guys can see. So we're going to call this thin black regions in this on the cloud. We're going to call this spider web, okay? And we're going to propose a hypothesis of how this works. So these big lumps, like I have here, so this is the surface and this white stuff is the cloud. So the surface, because it evaporates the ocean into the atmosphere, it creates buoyancy. So there's buoyancy because of latent heat into the atmosphere. So you have thermals going up, but at the very cloud top, you also have radiation that is cooling the cloud top, and this creates a negative buoyancy effect at the top of the cloud, and this creates sinking motions. And on top of this, there is another effect where the cloud meets the atmosphere. So the cloud can evaporate. So evaporating liquid into gas, this takes heat out of the environment, and this creates additional cooling. So this is evaporative cooling. So what I'm going to try to convince you here is that this the big lumps that you see here is because of surface buoyancy and radiative cooling on the top, and the spider web is because of this evaporative cooling when the cloud evaporates when it's in kind of a contact with the surface. The nice thing about the model is that you can manipulate the thermodynamics and the physics. So what we're going to do is we're going to manipulate our thermodynamic relations in the model, and for some simulations we are going to stop allowing evaporative cooling when essentially things change phase. So we're going to suppress entirely latent heat exchange when cloud evaporates and condenses. Okay, this is nice when you do modeling. You can do this stuff. You cannot do this in the real atmosphere, of course. So this is what I'm showing here. These plots are plots of the integrated liquid in the cloud. So this is a horizontal basically plot. This is XY, and the scale here is the integral of the liquid with respect to height. So top row is full physics runs, and then on the bottom row we same run, but we suppressed evaporative cooling. And this has a bit of an effect. Like you see, some of the lumps are there, but the spider web disappears. We did the same thing. In this case, we're just driving the cloud from the top by just cloud top radiation. So this is radiative cooling plus evaporative cooling, and you can see the big blobs, and you can also see the spider web, the thin canyons in the cloud. If we just do radiative cooling, you are just getting all the big blobs without the thin lines in between. And even in the just radiative cooling, you can still have like these regions. Some of these are called like cloud holes in the literature, where you have like these holes, like this. It's like a circular areas that are void of cloud. And we're going to do like something even more extreme now. We're going to take a full physics simulation, and we're going to run this for about 10 minutes. So we have a full physics simulation run up to hour 2, and we're going to make 2 more runs starting from hour 2 just for 10 minutes, one with and the other without evaporative cooling. So this is a Stratocumulus cloud deck that is about 5 kilometers by 5 kilometers in the horizontal long, and the resolution is just 1 meter. I think this is like the largest LES anybody has ever run on planet Earth. And if aliens have not discovered LES, maybe in the universe. It's about 20 billion grid cells. So full physics simulation on the left, no evaporative cooling on the right. And you can see like in 10 minutes, all the spider web disappears. So this is integral of liquid looking from the top. And this is even more impressive. So this is a cross section of the cloud, same simulation. So in just 10 minutes, all this stuff, all this these indentations at the top of the cloud, they just disappear. So everything else is active. We just change between the top and the bottom. We just change. We remove evaporative cooling from our system, and then you basically have like the big lumps, but you're missing all the little the spider web. Sorry again for being over time here. I just had to summarize a little bit here. So it's very exciting because these days I believe we have nice tools to tackle a lot of these issues. Even if you have like complex problems like Stratocumulus, you can still do LES. You can get nice results. You can get grid convergence. And then, as I said in the last 5 minutes, you can use these tools to discover cloud physics, or to ask questions about cloud physics and about other effects that you cannot do, obviously, this experiment in the real atmosphere. Thank you so much for the attention. It's nice to be here with you. Thank you again for the invitation, and especially Yuri for setting this up. So any questions, any discussion we can do right now.
Thank you so much, George. It was a brilliant talk. Thank you so much. Very stimulating. Loads of nice ideas, and I'm impressed with the power of your computations. We'll get into that. But let me first open to questions of the audience. And I will say em português, por favor, se alguém quiser fazer uma pergunta, por favor, pode me falar em português, eu traduzo. Se quiser escrever no chat, eu também falo para ele, tá bom? Or if you want to ask your question now, please go ahead.
Okay, so may I have a question?
Go ahead, Gustavo. Yes, of course.
So George, so you have a very nice results. So I have to ask some. You know, I'm more interested in microphysics, right, of clouds. And
yes,
you have a nice picture of this resolution sensitivity of your LES and the rate of precipitation, right? So you have one slide of that. And my question is, does your subgrid-scale model interacts with the microphysics or not? Because, for example, the presence of turbulence may increase the rate of collisions between droplets, right? These increase precipitation rates. So there are very complex physics at very small scales, right? At scales of the droplet. So my question is, do you account for that in this or not? So you have more a bulk scheme for microphysics, and then you just
yeah, so right now these processes are completely separated. So the microphysical scheme doesn't know about how much TKE is in the grid cell. It just goes and takes the mean fields and does its its assignment. But what you say is right. Like these are the effects that they should be they should be accounted for. And I mean the opposite is true. Also, if you have like if you have like microphysics and you have like rain and other hydrometeors falling, these also affect the TKE in the model and the stress that the fluid experiences in the cell. So these effects are not accounted right now in all of these simulations.
And and what about your feeling? Because you are a turbulence guy, and maybe do you feel that that microphysics plays a role, or do you think that turbulence modulates everything as you mentioned?
No, it does. It does play a role. Let me. Okay, I have. So hopefully you can see this, but it's like this is again one of these cases of precipitating shallow Q. And the boundary layer is different whether you allow the clouds to rain or not. If you allow everything, if you allow rain, you get this big this cold pools. If you don't allow rain to happen, get like a more of like the popcorn clouds. So this is it's a big thing. These interactions.
Yes, and yes, I agree with you. And maybe what about something not very drastic as precipitation, but you mentioned already this evaporative cooling, right? The effect in this entrainment at the top of your stratocumulus clouds. And also the microphysics is also important, right? Because of solving this entrainment and the influence on the evaporation. Also, I think that it plays a role. So
yeah, I agree with you. I agree with you. These are like all interesting problems. I mean, we did not have we don't have like a local like microphysics expert here. So it's we tend to work mostly on turbulence. But yeah, if anyone out there is a microphysics person and he or she wants to kind of like
jump in,
jump in, we want to these things are important.
So am I a matchmaker or not?
Maybe, yeah.
Yeah, great. So if there is a paper published joint by you and Gustavo and your teams, that our relationship started virtually in Brasilia at Teams. That has to be acknowledged on the publications. I'm joking, of course. Gustavo, are you done? You want more questions?
I have a lot of questions, but I leave it to other people to
okay,
ask.
all right. Does anyone have another question? Okay, so I'll have a question before I'll pass the word back to Gustavo. George, I was impressed by what you said about your LES simulation, 2 billion grid cells. I want to know a bit more. Go ahead.
20
billion cells. I want to know a bit more about the computing of that. Was it a supercomputer? How long did it take to process? How much memory? And also, when you showed not this one, but the other presentation, where you showed the grid convergence for delta x, for different delta x 2, 6, and 8, I think. Then on the following slide, you showed results for delta x equals 80. So you jumped a lot. You jumped, yeah, that one. So that's 2, 6, and 8. And then you had on the following slide, you had graphs that were generated for delta x equals 80 there.
Yeah.
So that's a massive jump on your delta x. So do you still expect to see to have converged results at that delta x? Isn't the truncation error already something very important?
Okay, so this is a good question. And we didn't have time to discuss this a little bit. So this flow here, this is the 248. So the flow here is very shallow. So this is 200 meters.
Mm-hmm.
This is the height of the boundary layer. But this flow here, the height of the boundary layer is 2.5 to 3 kilometers.
Oh, I see.
So what you're asking it's a great question because these numbers are dimensional numbers. So, like you say, you're right. It doesn't make sense to anybody, what they have to do, like 2 or 80. So the criterion is the ratio of the unresolved turbulence kinetic energy to the total in each grid cell. So I think I have it here. So this is or maybe I don't. I'm pretty sure. So there is a convergence criterion, and the convergence criterion is that the ratio of the subgrid scale TKE has to be less than 10% of the total TKE.
I see. So there is a physical criteria that locks your numerics.
Yeah. So you run the simulation, and the LES says, hey, like the unresolved TKE is about 30% of the total. Then in that case you must say, okay, so I'm not this is not the regime that my simulation will produce converged results, so I need to bump up my grid resolution. So if you're in the range of like 10 or okay, oh, these are the okay. So this is what I was talking about. So you make this line. So this is unresolved TKE to the total, and these are again like the same resolutions as before. Mm-hmm. So if you're kind of like getting below 10%, then it means that your LES is performing okay.
I see. I
mean, this is very model dependent. If you're running another model with a different turbulence closure, it might be, better or worse. Like the higher this number is, like the better, because you can run coarser resolutions and be accurate.
Yeah. I see. And how about the 20 billion less LES?
So the 20 billion in this, so it should be somewhere here. So the it's pretty well resolved. So this ratio, it's about, there's only about, if I can extrapolate, maybe there's only about like 1% of the TKE that is unresolved. But you have to remember that this is Kolmogorov scaling. So there could be like a lot of scales here on the right. Is because this is exponential. This is exponential to the k to the minus 5/3.
Yes.
So the integral is very small of the stationary left out, but the smallest scale can be very far from your grid resolution.
I see.
Because,
but it's been resolved anyway. It's not being resolved.
Yeah. So because the relation is exponential, so the TK is the integral of the spectrum. So you're basically you're left with just a tiny fraction of the integral, but the smallest length scale could be like pretty far from your grid, even at 1 meter resolution in that case.
I have another question before I open the questions again to Gustavo and others. So this is a very dumb, naive question, okay? Maybe it was my connection that I missed something. But you showed many results, and towards the end, you showed even very nice ways that we could see clouds. What is the mathematical, physical definition of a cloud? How do you define that region that we see on the graphs?
Oh, okay. I can tell you what we can have a lengthy conversation with Gustavo about this. But so when I'm plotting clouds in my images, I just put I have a threshold. I have this variable that is the liquid water, the suspended liquid water. Mm-hmm. So when I plot clouds on my plots, I have a threshold of 10 to the minus 5.
I see.
Kilograms of cloud liquid to kilograms of atmosphere. So this is kind of like the threshold. In reality, things are a little bit more complex. Mm-hmm. And in what your eyes see, or instruments, it's a little bit more complex because your eyes, they see radiation, they see the incoming radiation. So there could be cases where there is cloud, but it's very dilute, or the droplets are very large, so they appear transparent. So remember, the cloud droplets, like they don't have color, like water doesn't have any color, right? So they're white because they don't have any preferential wavelength absorption. It appears white to you because it reflects the sunlight without any bias, right? But this is a kind of, what is a cloud and not it's a lengthy scientific discussion.
Very good. Okay, Gustavo, do you want to ask any questions? Anyone of the audience? You feel free to ask questions, raise your hands. Have we lost Gustavo?
No, I'm here. So, okay. So if anyone, okay. So So George, so what you advocate is that to have a good large eddy simulation of a cloud flow, for example, so we need this kind of an anisotropic subgrid scale model, right? The dynamic one. This is what you advocate, right? So
I think it's important. Yeah, I think it helps a lot.
okay. Because we are using very simple things, and we have, you know, we are more interested in the interactions between the microphysics and the turbulence at subgrid scales. And I don't observe a very good resolution sensitivity, right, or convergence. And maybe that's a thing that we have to check, you know, to maybe to improve our subgrid scale model. So that's why I thinking about using something that what you suggest, right? So that's
okay. I mean, all of these tools, like even like the LES code, is available to everyone. You can go on our website and get it. So it's all of these cases are, and the code and everything is publicly available. So if you guys want to, I don't know, get this code and, you know, put your microphysics inside, or do the opposite, take the SGS model. You're free to do. I have to say one more thing here. So advection, how you do it, it matters. So this guy, this fully conservative scheme makes a big difference when you do turbulence, because it not only conserves the first two moments, like the mass and momentum, it conserves also TKE in the simulation. So it's not only non-dissipative, it conserves TKE. And when you have turbulence, like TKE is like the things that is getting processed, because you create a TKE, and then this trickles to like the small scales or sometimes the large scales. So it's very important to have like a nice advection scheme. Sometimes it could be like your advection scheme that is like messing up the LES.
okay. Yes, you know, we have what we have is a kind of an implicit LES. You know, we use the second order MP data scheme from Smolarkevich. Maybe you have heard about this, but we
Yeah,
can
I know
improve.
about that.
Mm-hmm. It should be less very non-dissipative, but yes, that's
But
what
if it's
we.
implicit, like it will
It
down
will
as much
be
dissipation as
yes.
it's required. So if you're
Yeah.
I mean, if you're doing neutrally stratified turbulence, this is fine. But if you're getting into like stratified situations where the the model is not supposed, because the Richardson number is too high, and you're not supposed to have any mixing from your SGS model. I mean, these models are, they're unaware of the Richardson number, so you might get into situations where this is like mixing too much. This model here, and it's also like the Smagorinsky, if the flow is like too stratified, it will shut off, like it will produce like an SGS tensor that is just zero. Like it will say, I see like no turbulence here. It's just like waves. So I'm not going to do any mixing.
Okay, nice. I understand. So perfect. So thank you very much for your answers. So George, I will keep in touch so that it would be nice to
Yeah,
invite you
definitely.
also for our in Warsaw in the Geophysics Institute. So it would be very nice if you agree. Okay, thanks. Okay, thank you very much.
Thank you.
Very good, very good. Does anyone have another question? Anyone want to ask a final question? George, I do have a final question. I was just very curious on the very first DNAs that you showed. You said that you imposed the shear. So are there rigid boundaries on that simulation? On the very first ones?
No, so these
Yeah, not
guys.
these ones. The very first ones. So
So
this is
what
the
happens?
comparison between.
So what happens here is that so this is what we call shear periodic.
Mm-hmm.
So it's a grid that is actually getting sheared, the grid
Yes.
itself.
Oh,
So
it's Lagrangian.
yeah, so the grid is kind of like getting kind of like it's like doing this with the
Yes,
flow.
sheared.
And then we, at every time step, actually, when it's doing this, and then we kind of like regrid on the vertical, and then we let it, because you cannot, if you keep the
Yeah.
distortion, it doesn't work for a long time. Yeah, this is how we do it. So it's actually shear periodic. So the grid is doing this, and then we'll grid on the vertical at the end of the
Right.
time step and do it again. And
But
we'll
there
grid
is.
in
Sorry, go ahead.
Fourier space, so it's a little bit easier to do the interpolation with less error.
But there is no flux on the horizontal boundaries. No fluid flux.
Here,
I can't see your mouse. My screen is. Yeah. So on the
no,
top and on the bottom.
There is a flux from here to here, so it's periodic.
Oh, so how? Oh, I see. It's fully periodic. So
The falsing is a bit discontinuous. That's why you get some of like this junk here sometimes, or this funniness, because the falsing is just discontinuous on this plane, but everything else is periodic.
oh, I see. So that laminar region that you see on the bottom when you decrease your Reynolds number, and you just see the stratification on the
This
top.
one.
So it means that on the bottom of this black region, there is the turbulent region on the top.
Yeah. This is it's periodic, so just keeps.
Oh, I can see it's the dark orange on the
Yeah,
top
so
there.
this
I see.
orange is kind of like coming into this orangey part here.
I see.
I mean, there's plenty of like intricacies going on here, so I would
Yeah.
everything I said, especially like in the beginning, like with respect to climate and everything, it's a kind of like a very I oversimplified
Yeah, of course.
a
Yeah,
little bit of
it's
discussion.
that's
So
absolutely fine.
if you go in the paper, you will see how to exactly kind
Yeah.
of like deal with all of these things.
How long do the simulations take?
These ones, they're not so severe because do I have the grid here? So this is
2000, isn't it?
it's a 1024 by 512. The Stratocumulus ones, we were running this for I think like about a month on it was like a 4,000 CPU cores.
4,000 CPU cores.
Yeah, so it's and each dump of data it's about a terabyte. So each
A
time
terabyte per very good.
so each time the code outputs like the 3D field, it writes a terabyte of data on the disks just like that.
My God. I'm impressed. These are really, really grown up toys. Not for kids.
I mean, yeah, if you end up like messing this up, you will burn all your like CPU time on the machine for basically nothing.
Nothing. Yes.
So when you do this, you have to be prepared because otherwise you'll
Yeah.
burn like millions of like CPU hours on the computer
On the
and accomplish
supercomputers.
nothing, and then somebody will come and ask you like what you did with the computer time we gave you.
Well, we generated some random numbers, so that's it.
Yeah, so it's not a. I mean, when you do this, you have to be
Very
you have to be like
careful.
a good citizen and use the resource as well because it's a shared resource. So if I'm not getting it, somebody else can use it. So whoever is doing this, has to be a good citizen to everybody,
Yeah.
and um, make sure that there's like some impact and some all of the results that are coming out of this are useful to everybody.
Fruitful. Yes. Very good, very good. So let me ask once again for the last time if anyone has another question for George. So I think, George, we are done with questions. So can I take this opportunity to thank you once again for this very nice talk. It was very nice to have you here. It is a great pleasure to learn a bit of turbulence modeling and cloud physics and climate modeling, and understanding a bit more of that from you in this very precise explanation of what's going on. So very clear. Of course, we don't see all the details, but we wouldn't understand all the details, but we understand the basics of what's going on. So that's very good. And I hope we can keep in touch. And I hope next time we meet will not be virtual, but in person. So that we can exchange more questions in a more friendly and easy way, right? George, thank you once again, everybody. Thank you once again for being here. George, you want to say something before we
thank you again, Yuri, for the invitation. I'm hoping next time we do this, I will be in Brasilia, and
yes, that would be great.
Also interact in person and hang out.
Very good. Yes, definitely. Yes, yes. Okay. See you, everybody. Thank you very
again.
much.
See you guys.
Bye-bye. See you next time. Bye-bye. I will stop the recording now.
Thank you. Bye.